Okay, welcome to lecture number 7. We're going to talk a little bit about threading and concurrency, and I do a little bit of asynchronous I/O that we talked about in class, but we'll kind of go over it one more time here. Threading and concurrency are kind of the easiest common way to achieve concurrency, and this is probably the easiest thing for Lab 1 to add to your web server. So we're going to walk through this a little bit, and I'll show you a couple of pieces of example code, but threading being kind of that POSIX thread way to create concurrency is it's seemingly simple but can get very complex, and to really get something done to the level of again getting paid for it or something that will grow and scale and last a long time really takes a lot of effort. So we're going to kind of scratch the surface of it just to show how we can achieve concurrency when we do socket I/O. We'll talk a little bit about asynchronous I/O. We've already talked about forking threads. So outside of that, really the pre-allocation, which again we covered last week, is your 4 main types of concurrency, standard in an operating system. And then, as we look to distributed systems and different ways to do it, everything kind of changes. But really today is really to talk about how we can achieve this through threading. So, what is a thread? Threads came about years ago, and until POSIX came around, which is kind of the common standard for source code to be portable amongst different operating systems. And again, source code being portable, not the actual executable. There was many different kind of variants of it, and it's funny because until we talked about threads, we didn't talk about a single thread of execution because it just was a thread of execution. But if you think of the history of going from a single process operating system to multi-process operating systems, that's really where we started to talk about, now having threads inside of a single program or in single process, and that's, kind of how this whole thing started. And I'll say it many times, I've said it before, we have to be very careful of threads because threads by themselves are still bound to all the limitations of a process. So as we look to, grow and create, much more concurrency, we still get kind of stuck and bounded with the fact that we have to still deal with the limitations of a single process. So, and I'll kind of walk through kind of the history and where we are today. But, it used to be back in the day that you could have a process with 1,000 threads and you could have a process with 1 thread and they get treated the same. So kind of wasn't fair, in how we were trying to do that. Now we do have mappings to threads in the kernel. So the kernel actually knows and manages threads a little differently today, but that's kind of the history of where all that came from. An operating system supporting threads is very common these days. 15, 20 years ago it was, Linux obviously did, and some other variants of Unix and Windows did, but it really kind of came about that it isn't just that it supports it, it's really more that it can manage it. And what I mean by that is in the first couple cycles of creating threads were a library, and it allowed you and your code to split things up, which did add some value if your process was the only one asking for the CPU. But if you had 20 processes all vying for the CPU at the same time, and you had 50 threads in one and one in the other, well, they didn't get treated all the same. So it's really more about the operating system and the kernel being able to manage your thread versus just being able to support it, because we can support it through libraries and there isn't a lot of value there. So the thing we also talk about when we look at threads is what really is a thread, what stuff comes with a thread. Because when we create a thread, we can actually rip apart different parts of a thread. So if you think of a single process that's running, a single process is going to have its own, like on the left, it's going to have its own code, data, and its own stack, its own memory. So if you have a global variable like int I, everybody has access to int I. If you go into a function and in the C language, you understand the difference between block and file scope. Things can sit in different places, but you have one common set of memory. You have one common thing for pointers. Everything is a single thread, but when you actually create multiple threads, everything gets a little stripped apart. The thread still has access to file scope, data, so anything that would be global. But everything that sits in the function itself, and the thread really kind of kicks off a function just to make it simple. And in that function, the function does kind of contain itself into its own memory. It has its own ability to create its own variables. And how it deals with the register and how it gets managed is all independent. So that's kind of what's shown there on the right with the process that's running and its own given stack as memory, as well as its registers as it's running. Now the code, the data, and the files on the top are still the same, and the files, being the file descriptors, the file table, that can be shared between, not only, everything across the process, but also across, when you do a fork and you have two separate, parent and child relationship, both of those have access to it. So, there's also something I don't think we're really going to talk about here, but there's the capability of creating thread-specific data and thread variables, which are not just the fact that they're in block scope. I mean, that's kind of a given. That makes a lot of sense. But you can actually create threads or create variables that are bound to a specific thread. When we talk about threads, we have to kind of think about, well, what does it mean to be a thread? What is it? How does it get created? How do we manage it? What happens? And the dynamic creation part really comes from the fact that a thread can be created at any time. So if you think of a socket, like what we could do and what you should be doing in Lab 1 is you're going to create a thread at any time when a new client comes in. So it isn't that we've pre-set up a bunch or we've got, one set up to go every 5 minutes. It's really there at the need of creating that thread. And in socket code, we really think about it from a client coming in and managing new client connections. But we could think about it, as load comes in, or if we want to have, sometimes we have worker threads that actually go off and do something different. Maybe they just do log file management, or they deal with, other forms of doing I/O or management of databases, things like that. So we can have them at any time, and usually when we talk in the socket kind of framework, we think about it from a client coming in. We create concurrency by having concurrent execution, and I always kind of step back and think about, okay, it isn't that they actually quote unquote do run at the same time, because only one thing's really ever kind of running in a CPU, and yes, we can have multiple CPUs and we can have different cores, and they could all kind of run independent. But what I mean is we have to think about the fact that us as humans cannot perceive anything, sub-second or, sub-millisecond. So if a CPU can, crank out billions and billions of instructions per second, doesn't really matter if they're kind of running in tandem or all at the same time. So we wanted to not really necessarily worry that much about, are they completely perfectly in parallel, but do they achieve the ability to do that? And that's really kind of what I talk about is, fairness in operating systems. Preemption is always going to be there. That's just something that the OS is really bound to. And the OS has kind of morphed a little bit from where it used to be in just really understanding where a process is to really understanding threads. And we can actually bind, and create what's called affinity to different CPU resources, mainly being registers, or at least the memory that is held, caching and all that in a CPU. So we know we have the capability, or we know that we should at least worry about the fact that things move around. And so, there is that cost of preemption, like the cost of changing, from one CPU to the other. So just something we need to keep in mind. The private local variables is what I was talking about, that can be created, that are not just the fact that they're bound to block scope, but that, there actually is variables that, we can define inside a thread itself. We share the globals. That's just kind of a, piece of languages, especially C, that, that's actually technically what's called file scope, and scoping of memory inside of the C language, versus block scope, which is technically either file or functions, or we can also do it inside of different blocks. depending on if it's kind of a looping construct or other forms of how we can break things apart. But normally it's file functions, kind of how we look at it. We've talked about shared file descriptors. Again, that's no different than a parent and a child still have access to the same thing. The difference is that all the threads have not only the connection to the file, but as one thread might move where you are in a file, it follows through with everybody, which is a little different than a parent and a child. Now, the coordination and synchronization functions are things that are, let's say, the advanced things. We're not going to touch on too much. We'll talk about mutex locks and some of the core capabilities, but really to do threads the right way, there's a lot of pieces that need to come into play because threads are somewhat fragile in a way. They're bound to all the process limits, so you can only have so many open file descriptors, which again is a big deal if you don't use close and sockets. It's also bound to the amount of memory a process can have. It's bound to the number of all kinds of different things inside of a process itself. And when all these threads are running, sometimes they might need to talk to other things. So we need things like semaphores or ways to know that we have locks, which are, we'll talk about in a little bit, mutex locks, to ensure that we're not, clobbering over, one piece of code or the other. So we'll dabble a little bit in the whole coordination piece of it, but, just keep in mind that, to really take threads to the, let's say, the professional level, it requires a lot more than what we're going to talk about here. Threads really do create a lot of efficiency, and they do it in a very quick and easy manner. Fork and exec or fork even by itself is a pretty heavy call to make. We talked about pre-allocation, and we'll talk about asynchronous I/O here in a little bit. But threads are a very quick, easy way to create efficiency, and for things like, let's say, a web server, it's a nice way to go have somebody else do the work, and you go back to accept, and if somebody else comes in right away, you can kick them off to another thread, go back to accept. It's not the optimal way, it's not the best way necessarily, but it's a very quick and efficient way to make it happen. And as we'll see with the code, there's not a tremendous amount of code that goes into doing this, and that's why I was saying for Lab 1, if you were to take the socket connection out of accept and send that to a function, you'll see that we're literally a few lines of code away from actually achieving threading in Lab 1. So we'll talk about that again here in a little bit. We do have the access to shared memory, which you could say is an advantage or disadvantage, or at least a caution, in that if I have access to everywhere in my memory and I have pointers running around and I do something kind of funky with passing a pointer to something that might get out of sync, or might have the ability to go do something, that could be pretty devastating to code, because things will kind of fall all over the place, and somebody could write a segment of memory that would kind of clobber other things that that are running. So but it's a blessing and a curse kind of thing, because there is the value that if you want to pass a pointer to memory that's 8 bytes of memory, that's nothing. You pass it off, it does all this work and manages the whole thing, and then goes away or comes back or whatever. There could be a lot of value in that. So kind of an advantage. Some of the disadvantages, though, are the fact that I don't think a lot of people spend enough time understanding the difference between a thread and a process, and really understanding what a process is and the limitations and how it's managed, all the way through the CPU scheduler, and some of the things that really come into big issues are all around this whole race condition idea. And a good example of that is functions that are known as thread safe, and the standard I/O library is actually one that we can deal with there, because if you think about the difference between, we talked about this a little bit, the difference between standard I/O or system I/O read and write with a file descriptor and standard I/O with a file object pointer, in that file pointer itself is a buffer. And let's say that we use standard out and we have 15 threads that all use the same thing. Well, they're all using the same buffer. So you could have 15 threads all at the same time print out through that same buffer, which kind of probably isn't what you want it to do. You want something to be a little more synchronized and kicked out. The bigger issue and one of the biggest problems that comes with threads are something called signals. Signals come in from various places. Normally they're sent in from external. There's ways to kick them off internal. But the problem with a lot of that is if the rule of thumb with threads and signals is if a signal comes in from external, all threads get it. Whereas if a thread kicks off a signal, then only that thread gets it. So it's kind of a dangerous thing that if the signal handler, the function that gets kicked off when a signal comes in, says to go print hello world, then if you've got 32 threads are going to print out hello world and clobber all of each other. So we have to think about, what does it mean to be sharing a buffer in something like standard I/O versus creating something that's what we call thread safe. So we take all that into consideration, and then we think about this lack of robustness, which is really not as much that it isn't written properly or that it's kind of loose. It's just the fact that us as developers and programmers need to understand a lot about what it means to use a thread outside of it just saying, hey, I'm going to kick off a thread and I'm going to achieve some concurrency. So we're only talking about C today. We'll be talking about Java threads coming up. And keep in mind, Java threads are an abstraction of C threads. So it's not like you couldn't do what we're doing in C as we do with Java. The difference is Java actually has a couple different ways of invoking threads, and being that it's object-oriented versus procedural, we have the capability to actually make something runnable and make a thread, unnamed or named, and there's a couple cool ways to do it, but we'll talk about that coming down the road. So, we're bound to a single process, which means that there's one file descriptor table. So if one thread opens a file, everybody has access to it. If the main function before it calls the thread opens a bunch of files, they have access to it. So it's a little dangerous, but it's technically not that logically dangerous, because let's say you wrote lab 1 and you made a logic error that said that everybody had write access to every file. You're going to know that pretty quick. You're going to get that fixed. It isn't one of those things that comes in, once every, 50 or 100 days and does something weird. The file descriptors are, kind of managed by the logic that you put in there, and it's really, I open, I read, write, and I close. So, although it's something you need to think about, it's not really a catastrophic thing like memory management, memory leaks, and things like that. We do think about blocking. Blocking is always a pretty critical issue, and the ability to fire up a process or a thread itself and do something that's blocking could and normally does only block that thread, but there is capabilities for you to do something that is process related or a process function that would then block the rest of that process. Kind of rare, not that possible, and again, usually in that category that you'll catch it in the first forms of testing and debugging, but again, it's that whole thing about thinking about the fact that a thread is in a process and it's still bound to everything that is a process. Exit is a big deal because exit is a function that is a process function. So by calling exit in a thread, you're essentially calling a process function which will exit the whole thing. So we just don't ever call exit in a thread. It just doesn't make sense. And again, all of these kind of fall in that same family of things falling apart early and being able to be caught as major logic errors versus something that'll come bite you down the road. Now, we do need to exit, and there's a few ways to do that. One is to just simply return out of a function as the compiler goes and cranks that through, and it knows that's running. We know that return returns to the calling function unless it's main, and main would then rewrite that as exit, and we're done. We do have a cleaner way to do it, which is a function called pthreadExit, and that's a way to kind of exit out. Now, that wouldn't just be the normal case. It wouldn't be the end of the function. You just let that return, or you just don't do anything, and it's done. PthreadExit might be something that you'd call in an error condition, or if you hit a part of your thread that just couldn't process anymore and you need to leave, but maybe you want a little more information on that thread itself instead of it just simply exiting or returning back. Okay, so when we talk about synchronization, the biggest thing we have to think about is you've got all these threads dynamically created, running around doing all this stuff, all quote-unquote at the same time. Because we have so many shared things, we have to worry about what's called race conditions, meaning typical easy example I always kind of throw out there is, take the example that I say I++. Everybody thinks I++ is, a form of an atomic operation. If I call I++, that's going to take I from what it is, add 1 to it, and we're done. So the example would be, let's say I is 5. So if I is 5 and I call I++, everybody thinks, okay, well, they're going to make it 6. Well, what if I have 1,000 threads all at the same time call I++? Well, it's such a small, quick, easy thing. Doesn't it just mean that it's going to say, well, take whatever I is, make it the next number, and move on? Well, there are atomic operations in operating systems, but I++ is not one of them. There's very few that are, and they are kind of dangerous if you write them wrong, because they basically mean that they take over the CPU and nothing else can come in. There's no preemption until it's done, so we don't want many of them. So as the example goes with I++, if you really think about what happens behind the scenes with I++, is you have to ask many questions. Number one, what is I today? Number two, where's the memory that I'm going to put the new one? And am I going to rewrite over, move a pointer? What am I going to do? I have to actually do the calculation to make it, 5 to 6. Then I have to write it and move it on. So there's many steps that happen in even something that simple, and I'm giving you the most simple example out there. But if all of them are doing it at the same time, let's say 10 of them all at the same time say, what is I? And they all say 5. Then all of them are going to write 6 instead of writing 6, 7, 8, 9, 10. So a lock is really the way that we use to ensure that these race conditions are, they don't happen. They're managed, and we can do them in a few different ways. But this whole idea of mutual exclusion really does kind of get to another thing that we use in operating systems called semaphores. Semaphores are traffic lights. If you're unfortunately going through a traffic light, you get a semaphore violation. So the idea of a semaphore really is that as long as everybody's playing right and you don't drive through a red light, then everything's going to be fine. Now, there's no concept of a yellow light. That's for us humans, but there's a green and a red. If it's green, you get to go. If it's red, you got to stop and wait. We don't like stop and wait because that leads to deadlocks and other bad things. So we use these where we need to. And the other thing I'll talk about a couple times here is that we don't want a lock to be something that we lock at the top of a function and we unlock at the bottom. We only really want to lock around the critical section. And we also want to name these critical sections. So if there's a critical section A, B, and C, then create 3 different locks and lock them separately. Otherwise, what you're doing is if you use threads and you use locks and you lock the top and you unlock the bottom, you've wasted the whole point of doing locks because it's still going to have to wait for everything else to happen. So mutex locks are the way we deal with threads. Semaphores are how we deal with between processes. And there's really only a few things that we need to do with this, which is initialize, lock, and unlock. And the initialize is that whole thing going back to what we did with sock adder ins and different things, B0s and mem sets. And we need to start from something that is known, which is basically always all zeros. We don't want this thing to be set up in a weird fashion that says, oh, I know you want to lock, but let's just go ahead and just not lock, because that's one of the settings we can do. Okay, this is one of the ugliest functions you've probably ever seen. The reality is it does boil down to something much easier and much simpler. But because we're dealing with a procedural language that does not support polymorphism, we have to create this function that basically says I can take kind of anything I want and do anything I want, and I can pass anything I want. So the way it kind of breaks down is we've got this pthread create that returns an int. This int is going to be 0 if RK or error number on failure, which is just not a 0. We use p error to find out what that error is. We've got this pthread pointer restrict thread this is a function name. So we'll just see this is just simply a function name. But we need to prototype it for any function name. So we don't want anything to say that it's going to return an int or a void or float or whatever. We've got our attribute set, which is here. And then we've got our actual, I'm sorry, I got that wrong. This is the thread ID. So this is something we're going to create. Then we've got our attribute set. This here is the actual function. So a void pointer return, which just means anything. Function name, which is anything, and anything it can take as an argument. These are the actual arguments passed here. We don't pass them here. Again, just the negative impact that polymorphism gives us. So as we see this get built, we're going to create this pthread TID thing. It's going to get passed here. An attribute set, which can be null, and an argument set that can be null, and then the function name. So as functions go, we talked about exit, and the way to call pthread exit is this function here. Now, there's no real point of dealing with the return of it because there's nothing we can do about it. If you call pthread exit and it fails, nothing you can do. So that's why it's not in there. But this is the what they call the graceful way to exit a thread. So normally it's the way you call it. Now, graceful doesn't mean that it isn't exiting because something failed. I mean, that's still a healthy reason to do that. But this is really all about just exiting in a way that isn't a return directly to a function with no extra pieces to it, which is its value, versus calling exit and blowing out the whole process. Processes have IDs, threads have IDs. So a thread by itself has an ID. It's a very large number that doesn't mean that much to you as a user, just like memory addresses don't. It's interesting to know if you want to know if a thread is the same as another thread, which is actually one we have to ask a question of, pthread equal. And pthread self is kind of like get PID, which is our way to see what a process ID is. We can spit that out. Now, normally what we do with this more than anything is we spit this out to a log file. Thread ID 41069274221 did this, or was created, exited, whatever. I kind of chuckle at that a little bit because what does that mean to me as a user? There's nothing I can do to change that. But if I wanted to follow necessarily what a thread did and it was logged properly, I could actually look at it that way. So that's really the biggest value of this is this thread ID. And it's also something we can use to go cancel a thread because we have to have a handle. We have to have a known way to own it. Threads actually have two flavors. You can join or keep it detached. And the concept around it is there is a way to create a thread that isn't necessarily quote-unquote running on its own. The default is to make it do that, and we'll see that when we get into the code here. But we really do want things to be detached, and we want things to, run in their concurrent state. That's the biggest value of it. But there are reasons, let's say we're doing logging or we're doing something else where it doesn't necessarily make a ton of sense and doesn't have a lot of value to run detached. It might even cause, other race conditions on other, non-detached threads. So that's our capability here. So that's really what pthread join is doing for us. So pthread cancel is our way to kill another thread. Now, to do this, you have to have a management function that knows what threads are invoked, what things are happening, and you have to have a reason why. So is it that you have a timer on all your threads that if they don't report in within 4 minutes that you kill them because we know they're doing something in TCP that has a 4-minute timeout? Maybe. There's been a few use cases I've used things like this in the past. But the thing that's interesting is if you build something that's a daemon process server or something that's going to run forever, and you don't manage the threads are kind of, in a way, a glorified memory leak because maybe a thread runs and just gets into a weird state and just sits there forever. I wouldn't say that I've seen tremendous amounts of code that deal with all this in a very, clean fashion, which is why some operating systems need to be rebooted all the time. But this is really something that needs to be understood, and definitely a part of this is kind of how we manage threads. So I put this little table together to kind of give us an idea of between what a process will do and a thread will do, to kind of understand that a fork is a lot like a pthread create, an exit, or even a return is more like a pthread exit. Wait PID is, and there's many waits out there, but they're really, kind of our way to get a signal, and we know that when something is, gone, like a child process, we get a signal. We have this concept, and we probably haven't talked about it in this class, but this function called add_exit, that you set up these functions in order that get executed in reverse order. So if you set up 1, 2, 3, they're going to be run 3, 2, 1. As the process is terminating, as long as it's not a seg fault or something that blows up, when the process exits gracefully, it will actually execute other functions. So if you want to spit out, something to, trunk a log file, or send a message out to somebody, or, do something, you can call these add_exit functions. Threads have the same kind of idea, and what's called they have a pthread cleanup push and a pop. So it'll go ahead and push things onto a queue and do that, first in, last out, same kind of deal. I talked about get PID. Get PID gives me the process ID of my current process, and pthread self is my way to get my thread ID, my TID. And if I call an abort, that's a signal of an abort, versus a cancel, which is kind of that kill in a way. So for mutexes, again, these are the things that are locks. We need this pthread mutex init, the one in the middle, to really kind of set things up. We don't normally use necessarily destroy, but if we do have a lock that we want to manage in a different way, we have the capability of destroying it. The piece that's really interesting about this, and this is where you really start to see different levels of C code, as well as how people thought about, how to put the construct of a language together. But, the idea is that we have this attribute set here, which again has to be set up as initialized. Anytime you've got something that's beyond kind of those primitive, native, in float and whatever, normally we always want to use those, in the fashion that we know that they're set up as default. Anything that's of, more of an abstract type, like a structure, we got to clean up and initialize. So, so we can use null, which if you think about what null is, that's zeros, so that's an easy one. Or we want to go in there and kind of clean that up. I'm not showing it right here just now, but this is our kind of way to, as we initialize it and we put in the attribute sets, again, we want to clean it up. So locking is kind of interesting, because we don't like necessarily locking, because locking is a blocking call. Blocking calls lead to deadlock. Bad things can happen from that. If you get to a point where you really, really don't want a deadlock, or you just know that there's a bad potential for it to happen, there's actually a function called a try-lock. Now, a try-lock is non-blocking. It will kick out an error of busy, or, it is locked, is the answer. The problem with this one is a little bit of logic. If you say, I want to try the lock, and it's busy, what do you do then? What do you do then? Do you just sleep for a while? Do you try again in 2 seconds, 5 seconds? Do you have like if you've ever seen Google Docs or even Google Email, when you lose your network connection, it'll try it for 4 seconds, then it'll try for 8, then it'll try, it kind of keeps adding on, just kind of saying, hey, why would I keep trying every 4 seconds if it didn't happen in 4 seconds? Let's go a little longer. This is all up to you. You have to figure out what it means to you to go back and try again. But it's kind of an inefficient way to do it. But, there has been and there is a need for it. We do have these capabilities in almost all the other forms of things that do blocking by passing a non-blocking mode to it. Even open by itself has it. Function control. Some of the, the low-level system I/O things have it. So normally it's lock and unlock. I want it, I block on it, and I have it, and when I'm done, I unlock. One of the ways I always kind of remember these locks is there's a golf course up in where's that, Nisswa, that called the Pines, which is on Grandview Lodge, and there's a hole where you go out there and you can't see it goes out about 50 yards and it just drops off a cliff. So you can't see past there, and you're not supposed to go out there and look, because that's actually in play. So you're supposed to tee off. So they have a little red and green light, kind of a little traffic light that sits there. And the idea is don't hit when it's not green. So if it's red, don't hit. Because that means there's probably people down there. Now, that doesn't mean there's people down there. It just means it probably is. I've been there a few times where the red light stays on for, 10 minutes because the people forgot to turn it off on the bottom. So the point of the story is there are things that are set up to lock and unlock. But if your code doesn't play right, you could actually set it up that, the inability to unlock, if you have other things that could happen and skip that part of the code, conditional statements or whatever, could be pretty catastrophic. So when we think about these, any forms of locks, what we think about is what's called a critical section. And a critical section is the thing that you cannot have more than one thread or process or whatever modify at the same time. And by modify, I mean write. We don't care about reads, we only care about writes. So I++ is a perfect example. We don't necessarily care about the fact that everybody's reading what I is, but because they need to increment it and write it, we know that I is a critical section now. So anytime we deal with I, whether it's, if we're just printing out I, who cares? Just print it out. It is what it is at that point. If we say I++ or I equals I plus 6 or I equals J plus 9 or, whatever, that's modifying it because we're writing it. And every time you do a write, that turns it into a critical section if that's something that more than one entity, more than one thread or process or whatever can do at the same time. So this is really where we need to bound it around that. But what you want to do is lock, do I++, and then unlock right after it. Don't start the lock at the top of the function and then unlock at the bottom, because you've kind of destroyed the whole point of concurrency. The other thing that you'll see that people do, and I'll try to show you in code here, is when you put a lock on I, and you put a lock on J, and you put a lock on K, well, that should be 3 different locks because they have nothing to do with each other. And I see that kind of time and time again where they'll use the same lock on each one, which is kind of silly because if they have nothing to do with each other, there's no reason to lock all at the same time. Okay, so let's go look at a threaded server. So I think this is right here. And just make sure this is the right one. Pretty sure it is. Yep. So if we look at this code here, a couple things to note. Here's going to be our thread ID. So a lot of times you see it as TID. Here's our attribute set. Now again, we haven't done anything with these yet. All we've done is just defined them. So TID, sometimes they call this ATTR. Really where we start to look at this threading code is right in here. So we're going to do this attribute init on TA. So this is the mem set, the cleanup, let's make sure everything's clean and nice. We're going to set it in that detached state because we want it to run independent. And then we're also going to go through and set up the mutex. Now, the thing with the mutex that's a little strange in this code is they actually plugged it into this structure here. So this is a stat structure, and what they're trying to show is that you can use a thread for concurrency, but you can also use one for management or logging or whatever you want as well. So a little weird to kind of have it independent, but that's why it's part of this stat structure. So let's not get that totally confused. So here's our setup. Then we go create this thread. Now the thing we're doing with this thread is this is the printing the stats. And we'll get to this function in a second. This has nothing to do with the general dynamic creation. This is just one that just runs on its own. And what we're basically saying is, let's go kick this off with this thread ID here, which we'll use again, this attribute set, which we'll use again on this function. Now, most of the time you don't need all this stuff up front. They're just prototyping this to not have errors when they compile, but normally all you'll see is pure stats. And again, they just said zeroing here is null for the fact they don't care about the there's nothing past a PR stats is what that's doing. Here we get into our while loop, so this is going to be this code running forever, and it's going to spin around here. And here I'm doing my sock, comes out of accept, so I'm going to block on accept, I come through, and basically all I'm doing is I'm calling pthread create again on the same thread. So it's weird when I see people create a lot of these because thread IDs are all independent. It doesn't really matter if, it's TID1, TID2, TID3. Our attribute set, which just says how I want to treat it, which is detached, meaning go run by yourself. And then every time this thing runs, I'm going to call TCP echo D, and I'm going to pass it this SSOC. Now this is one of the most critical, most important things in all of this code. I cannot pass this as a pointer. I'm passing this as its native integer. Forget the void pointer here, because it's not a void pointer. This is actually, it's not the memory address of it, it is actually the socket. It's the int that comes back here. The reason this is important is, let's say we kick off 50 threads, and we keep changing the value of the same pointer that we're passing around, then everybody's dealing with something different. And I don't know that this would even compile if we did it wrong, but this is a critical issue. So we know the difference between when we pass a pointer that could change all the time versus passing the literal int of 3, 4, 5, 6. Once we get into this function, we're going to take that file descriptor here. We're going to go do all the things we do, and we're going to basically go spit that out. Now, the thing that's interesting here is exactly what I was saying before. I'm locking and unlocking on one thing, which is this stats structure. And this is kind of an interesting way to do it, because what they're doing is they're saying, at this point, I just want to increment the count, which is one of the members of this. So if we go back up here, the count is here. So that's only one thing that we're actually dealing with. But I love the fact that it locks and unlocks right around it. Then it goes and does some other stuff. Well, it reads from the file descriptor, does some stuff, then it does another lock, and it changes the byte count because it knows that. And it's very crisp and just around the things it needs. This is a critical section. This is a critical section. Most people, what they would do is they would set up the lock up here, they would unlock down here, and it destroyed all value of concurrency. Because it could be that if you think of 50 of these things, one might be waiting here for a lock, one might be waiting here for a lock, one might be waiting here for a lock, but as soon as anybody gets it, they can call it kind of all iteratively move along. So, lock and unlock, love it, all good, moving along. We've read, and then we write. This is just an echo, so it's nothing super fancy. We read, we write, we close, and then we do another lock, and we kind of put some other things in there as we're moving along. And we return, which kind of again comes back up to here. So that's kind of the dynamic thread creation thing we talked about in the beginning. And then at the end, this is something that actually, I think it's every 5 seconds or whatever it is. It sits in this loop, and it will hold for every 5 seconds. Again, it has to lock because it has to know that I want all the stats to be clean. So if all this stuff is going on up here and you got 1,000 threads all running at the same time, we want this guy to come in at this point, lock here, and it has to lock for this whole thing. So even though I told you not to do it, you have to do it here because we're going to go calculate this stuff and we're going to print this out. Now, this isn't unbelievably critical that if it said, oh, there was 1,038 threads that ran for 4 minutes and 42 seconds, that there would be a big difference if it was 4 minutes and 43 seconds. But some things, like Wall Street and stocks and all that might be that way. So that's just kind of what they're doing here is they're just saying, look, every 5 seconds or whatever it is, we're going to spit out these stats, and we're going to see what's going on, whether this is to the console, but they could log it or whatever. So this is kind of a nice, clean, easy way to do this. Now, let's shift into second gear here and talk about lab 1 for a second. If you get to the point where in your code you're doing this and you get in a client, and if that client, this SSOC, is something that you're just going to go send to a function, and that function does something with it, moves on, this is exactly what you're going to do. You're just simply going to call this pthread create here. We do not have a need to do locking because nothing in this is going to be, there is no critical section in how we're defining our web server. So really, this is why I keep saying that the thread piece of it is the easiest piece. And the hardest part would be if you don't have the SOC being passed to a function, you just have to pass it to a function. And that way, it's just like this here. It's going to accept it. It's going to go do the work and move on. And the point of this is that once this is called, this code goes back up and calls accept and sits on accept on blocking. I'm going to stop this one here and we'll start up again with pre-allocation.